When David Tennant played Hamlet in 2008, he used the real skull of a dead pianist in the grave-digging scene, where Hamlet discovers the skull of a court jester he knew as a boy. Alas, poor Yorick, I knew him, Horatio. The pianist was Andrei Tchaikovsky, not to be confused with the composer Tchaikovsky, and this pianist had requested that his skull be used as the prop of Yorick's skull in the play Hamlet. I don't know why he made this request, but I do see the grave-digging scene as a series of veiled musical ciphers. The presence of Horatio, with the root word ratio in his name, points to the fact that all three intervallic ratios of Ptolemy's tense diatonic tetrachord are encoded into this scene. Those ratios are 9-8, 10-9, and 16-15. The 9-8 ratio is alluded to in this line regarding the 8 or 9 years it takes for a body to decompose. This ratio also has a numerical value you can find by dividing 9 by 8, or 1.125. The scene's setting of the grave is a veiled reference to the 10-9 whole step ratio, which is known by all sorts of names, one being the grave or lesser whole tone. That's because its numerical value is lower. 10 divided by 9 is 1.11 repeating. The semitone interval of 16-15 is harder to see because the octave value for 15, being 30, is used against the tonic of 16. Calculating this ratio, we get 1.066 repeating. Two skulls in the grave-digging scene are described by Hamlet as having sung music. Regarding a skull the gravedigger is tossing out as he digs down, Hamlet reacts, saying, "That skull had a tongue in it and could sing once." Yorick was also remembered for his songs, and it was these intervals of Ptolemy's tense tetrachord that the well-known music theorist Zarlino described as the only tuning that could be reasonably sung. A reference to a musical ratio occurs at the play's beginning as well, when Horatio, representing ratios, first appears with Marcellus. Horatio tells Hamlet very specifically, "2 nights together had these gentlemen, and I with them the 3rd night," referencing 2 and 3. Marcellus supports this 3-2 ratio, as he's an allusion to Marcus Claudius Marcellus, the commander of the Roman army that sacked Syracuse. This battle resulted in the death of Archimedes, and it was Marcellus, feeling guilty about this, who then built Archimedes' tomb, which prominently featured another geometrical and musical ratio, 3-2. The story goes, according to Plutarch, that Archimedes is said to have asked his kinsmen and friends to place over the grave where he should be buried a cylinder enclosing a sphere, with an inscription giving the proportion by which the containing solid exceeds the contained. That proportion or ratio was 3-2, the volume of the cylinder being 1/3 larger than the volume of the sphere it contained. This is also the musical ratio of the perfect fifth, or the mies of the scale. What's interesting to me about Hamlet's allusion to the Ptolemaic tense tetrachord is that it indirectly produces another ratio that solves a musical problem. Music has always had an inherent tension between fifths and octaves, between the tripling of frequencies and the doubling of frequencies. Intervals based on the tripling power of 3 are ascendant, while intervals based on the doubling power of 2 are functional. And we've been trying to find a way to marry these two powers, to make music both ascendant and functional for thousands of years. The power of 3 is expressed in Pythagorean tuning, but it distorts the octave and the power of 2. So the solution has been to redeem the octave and its power of 2, using equal temperament tuning based on the square root of 2. But it's not a tuning solution, it's simply a compromise. Many of us are unaware that we failed to find an actual solution, and that our musical tuning is flawed and discordant. We're unaware because we're just used to music the way it sounds. We grew up with the tempered scale, and few of us perceive the beats, the throbbing conflict of frequencies that occur with the distorted intervals of equal temperament tuning. But it turns out that the difficulty in tuning music isn't really about incorporating fifths and octaves. In my research, I discovered that the harmonic series does that just fine, producing just fifths alongside just octaves. But the tuning problem does involve melding the powers of 2 and 3, something that's simply impossible to do. And it can be shown at its most atomistic level when we look at the inherent problem with the note of F. In the key of C, F is the perfect fourth, but it's not the position of the fourth that's the problem. Other notes hold that position in other keys. For example, G is the perfect fourth in the key of D, and the problems we see with F aren't a problem for G. As a note, F is generated fairly late in the harmonic series. As you can see, the 8 structural beams generate first: C, G, E, B flat, D, F sharp, A flat, and B. Then the chromatic scale fills in the rest of the notes, with F not showing up until harmonic 21. F is also generated last in the circle of fifths. And like C, the note of F has no accidental preceding it. The accidentals are the black keys on the piano, all the sharps and flats produced together here on the circle of fifths. The lack of an accidental is the reason that F, according to the philosopher George Gurdjieff, causes a retardation or slowing in both the ascension and descension of the scale. He writes that the scale vibrations develop in a regular way only for a certain time. But at a certain moment, a kind of change takes place in it, and the vibrations, so to speak, cease to obey it, and for a short time they slow down and to a certain extent change their nature or direction. The same retardation occurs at the end of the scale when B returns to the octave of C. But again, this retardation occurs in all keys. It's only F and C themselves that lack an accidental predecessor. The ancient scales listed in this article, by archaeomusicologist Richard Dumbrill, begin with D rather than C, and I believe this was done to avoid the note of F and its tuning problems, as the major third off D is instead F sharp. But what does it mean to change from the key of C to the key of D? On a piano, it looks like this key change is just moving up a notch, a whole step notch from C to D. But that's deceptive because this key change, this modulation, is from the key of harmonic 1, C, up to the key of harmonic 9, D. We're moving the key signature out of the power of 2, the system of 1-2-4-8-7-5 on the Mobius circuit, and into the power of 3, the 3-6-9 system, of which 9 is the apex mies. And this is how the ancients constructed the scale, with the note or string of D on the lyre, which is harmonic 9, at the mies or center of the instrument, with fifths and fourths radiating out in both directions. But simply switching over to the key of D was just a temporary fix, a way to avoid the note of F altogether. It certainly didn't fix the problem. Over the last few months, I realized that I had missed the significance of something in Plato's Timaeus, where the demiurge constructs the world soul in the same way one might tune a musical scale. Plato tells us that the demiurge generates 3 doubles on the left side of this lambda, and 3 triples on the right. After that, he, meaning the demiurge, went on to fill up the intervals in the series of the powers of 2 and the intervals in the series of powers of 3 in the following manner. The manner turns out to be calculating both the harmonic and arithmetic mean for each interval on the lambda. The harmonic mean can be calculated by the formula of 2ab over a plus b, and placing the harmonic mean for the interval of 1 and 2, we calculate that 2ab over a plus b is 2 times the product of 1 times 2 over 1 plus 2, which gives us 2 times 2 over 3, or 4 over 3, the ratio of the perfect fourth. On a piano, that would be from the note of C to the note of F, the problem note. So the harmonic mean of the octave interval is the ratio of the perfect fourth, 4:3. But look what happens when we fill the intervals on the other side of the lambda. The harmonic mean of the interval between 1 and 3 is the ratio of the perfect fifth, 3:2. So while the harmonic mean in a doubled interval is the perfect fourth, in a tripled interval, it's the perfect fifth. So that's kind of fun. But returning to the perfect fourth as harmonic mean, the problem surrounding F is that none of the 3 major tuning systems, Pythagorean, harmonic, or equal temperament, tune F as a perfect fourth at the harmonic means value of 1 1/3. Let's find out the value of F, or the perfect fourth, that's generated when stacking fifths. Notice that the first 6 notes, which aren't in scale order, are the white keys on a piano. These 6 white keys are generated together. And then the black keys, the sharps and flats, known as the accidentals, are generated next, also as a group. But there's one white key still to be calculated, the note of F, which waits until the very last position on the circle of fifths. If we use its calculated value of 345.99, the resulting octave of C will be 518.98, about 7 Hz sharp. And that sharp imperfect octave is the Pythagorean comma. But remember that Plato's first harmonic mean generated an F on the left side of Crantor's lambda with a value of 1 1/3. If we scale that up to this octave, the resulting F value is 341 1/3. Inserting this value for F into the circle of fifths, it's the precise value we need to then generate a perfectly doubled octave at 512. So in the key of C, using the harmonic mean for the perfect fourth doubles the octave when stacking fifths. Essentially, though, we can't stack F as a fifth. Instead, we have to take a new approach by calculating the harmonic mean and filling that first interval just as the demiurge does. Another way to generate F at 4:3 is to stack the 3 ratios of Ptolemy's tense tetrachord. And this is what I was alluding to when I said it directly produces another ratio that solves a musical problem. That ratio it produces is 4:3. To me, the fact that these 3 ratios are hinted at in Hamlet's grave-digging scene isn't all that unusual. As a Baconian who believes Bacon was at least involved in the writing of the Shakespeare plays, I've seen not only musical ciphers, but also musical explanations in Bacon's work. When stacking fifths, we apply the ratio of 3:2 over and over again until we reach F in the last position. But if we stack 9-8, 10-9, and 16-15, we generate F at a ratio of 4:3 off the tonic in the fourth position. So let's see what that looks like. C at 256 multiplied by the 9:8 ratio, or 1.125, equals 288, the harmonic value of D. 288 multiplied by the 10:9 ratio, or 1.11 repeating, equals 320, the harmonic value of E. Up to now, we've been using the intervals of the harmonic chromatic scale, but at this point, we have to deviate from that. We have to now shift over to Ptolemy's tense tetrachord, replacing the harmonic F2E semitone ratio of 21:20 with the harmonic C to B semitone ratio of 16:15, or 1.066 repeating. Multiplying 320 by this value, we hit on the fixed value for F, 341.33 repeating. So while this isn't a harmonic frequency value for F, it does use a harmonic ratio. But a different one. We're applying the ratio of C to B to the relationship between F and E. And we can double-check this by simply multiplying C at 256 by the 4:3 ratio of 1.33 repeating, and also arrive at 341.33 repeating. But it's after this takes place that we encounter the small imperfection that the 4:3 ratio creates. And with this small imperfection, we see something strange, something that looks like a cipher signature from the mind that designed this tuning matrix. It's a strange number that seems to allude to the relationship between F and G, between the perfect fourth and the perfect fifth. We already know that the perfect fifth off C at 256 must be 384. That's the value we get when stacking fifths, as 256 multiplied by 3:2, or 1.5, equals 384. And that's also the value we get for G as the mies of the harmonic chromatic scale. C at 256 plus C at 512 equals 768, and divided in half, that also equals 384. But the value of F corrected with the harmonic mean can't generate the note of G exactly. It comes close, but 341.33 repeating multiplied by the ratio of 9:8, or 1.125, is 383.99 repeating. Almost there, but not quite. It's close enough for tuning a musical instrument, but the precise math behind this is something we shouldn't ignore. When we divide the higher note by the lower note, we arrive at the value of the ratio between them. So if we divide G at 384 by F at 341 with 100 threes after the decimal point, we end up with a number incredibly close to the 9:8 ratio of 1.125. But it's 1.125 with 99 zeros after it, and then a strange number tacked on the end, 10986328.125. This strange number isn't just randomly showing up at the end of this long decimal. If we divide 384 by 341 with only 95 threes, the strange number shows up again, but earlier. The smallest number of decimals I've found just goofing around with this number is when I plug in 97 threes. The basics of the strange number are that its value reduces down, using vortex math, to a value of 45, which again reduces to 9. The 45 speaks directly to the relationship of the perfect fourth to the perfect fifth. And 45 sits at the mies position between F at harmonic 42 and G at harmonic 48. But what's most noticeable here is that the arrangement of 42, 45, and 48 fits perfectly into the 369 system on the Mobius circuit, with G's value of 48 reducing to 3, F's value of 42 reducing to 6, and the value of 45 reducing to 9. and both 45 and the strange number show up in the math of digital data transfer as well. It appears as the value of megabits that can be transferred in 1 minute at a transfer rate of 1,440 terabytes per minute, with 1440 being the fifth octave of 45. Another relationship between the strange number and 45 is that both of them, as reciprocals, where one is divided by that number, produce a repeating digit of 2, which is shown here in the online encyclopedia of integer sequences. Notice that in the list of numbers producing repeating 2s are several octaves of D at harmonic 9. In fact, every even number listed here is an octave of D, making these numbers multiples of 9. However, the most interesting repeating decimal is produced by the reciprocal of 27, not an octave of 9, but its triple, producing the note of A that scales up to 432. This reciprocal produces a repeating 37 separated by zeros, and it just so happens that harmonic 37 produces all the angel number or repeating 3-digit harmonics. But I digress, and we should return to the problem note of F and the ratios historically used to overcome it. I'm going to begin with the end and show a scale that I believe ticks all the boxes, solves all the problems, and produces a workable scale. In my opinion, the solution to the mistuning of music is found here on the bottom of this slide. So if we have a scale laid out up here, the spaces between each note will be represented by various ratios in columns down this slide that we can compare with what I think is the correct order of just ratios down at the bottom. The legend for this grid is that aquamarine is a just ratio. White is a just ratio, but in the wrong spot. And this yellow color is an unjust ratio. The Sumerians produced a 9-tone scale, or ennead, the frequencies of which Dumbrell includes here. As Dumbrell writes, this tuning was not an ascending or a descending alternation of fifths and fourths, but a projection of fifths and fourths from the central note D. In my view, the fact that the Sumerians placed the tone of harmonic 9 at the mies of their scale is extremely significant, as we also see the 9 in the position of mies on the Mobius circuit. So let's take a look at the original Sumerian ennead, shown on the left as a normal scale with an extra note on the bottom. The Sumerians used 2 values for E. The first was the harmonic value of 640. Its octave would have been 1280, but instead, this scale pushes the octave E up to the Pythagorean value of 1296. These 2 E frequencies illustrate the difference between harmonic E at 80 and Pythagorean E at 81, a relationship expressed in the Phantom of the Opera between Christine Day and the Phantom. The Sumerians also tuned the C slightly sharp, though in the key of D, this note should have been C sharp, not C. The reformed Sumerian ennead pulled the second E value back down to the harmonic value of 80, and also pulled the sharp C down to the harmonic value of 1024. But unlike the harmonic series, which starts its scale with the note of C, both of these Sumerian enneads are based on the note of D, and I believe this was done to avoid the problem note of F. As I said earlier, the key of D major skips over F altogether, as the major third off D is F sharp rather than F. And in the frequencies Dumbrell lists for the Sumerian scales, there is no frequency correlating with F. Harmonically, F and F sharp in this octave would be 672 and 704 respectively. The Sumerian value of 720 is sharper than harmonic F sharp, so it's not correlated to the note of F at all. All but one of the intervallic ratios of the first Sumerian Ennead are justly intonated. The one that's not is the one in yellow producing the sharp C, 27 to 25. And all of the intervallic ratios in the reformed scale, 9 to 8, 10 to 9, and 16 to 15, are just. But in both Enneads, they're out of order, with the order shown at the bottom. The only ratios in the right spot are surrounding the note of G, and so, off to the left, both Sumerian scales get a 2 for having two correct ratios in the correct place. Next is the Babylonian scale that Dumbrill said developed around 2000 BC. This Ennead was identical to the original Sumerian scale, so the Babylonians must have missed all the reforms. Anyway, they joined the Sumerians with two correct ratios in the right spot. In the Pythagorean stacking of fifths, the scale switches to the tonic of C rather than D, meaning that the perfect fourth is now F rather than F sharp. Generating the first fifth off the tonic, the ratio produced is 9 to 8, and that matches with the correct ratios listed at the bottom. This is the first scale we've seen to do so. Stacking fifths produces three ratios marked in yellow that are very close to correct ratios, but ever so slightly off. For example, between the major third E and the perfect fourth F, the interval that should be 16 to 15 ends up being 16 to about 14.98. This scale, like those before, scores only two correct ratios in the right spot. Dumbrill lists these values for a Greek scale, a Pythagorean hypodorian using the tonic of D, and we can see that it also failed to recognize the phantom's 10 to 9 relationship between the major second and third that prevents the Pythagorean comma. Instead of using the 10 to 9 ratio, the Greeks used the unjust interval of the lemma, 256 to 243, to correct for the comma. The lemma is what Plato calls a necessary leftover in Timaeus. The Greeks used the Pythagorean value of 81 for E, which forced them to overshoot the Sumerian value of 45 for F sharp, jacking it up even higher to 729, which is roughly 45.5. In my view, their use of the lemma took them a few steps backward from the higher musical understanding of the Sumerians, and I'm reminded of Sir Francis Bacon's dim view of ancient Greek wisdom, summed up when he wrote that, "For its value and utility, it must be plainly avowed that that wisdom which we have derived principally from the Greeks is but like the boyhood of knowledge, and has the characteristic property of boys. It can talk, but it cannot generate, for it is fruitful of controversies, but barren of works." The Greeks used only two intervallic ratios, and only one of those being just. But their use of the lemma did allow for the 9 to 8 ratio to precede the major sixth, so this hypodorian scale scores a 3. Next we'll look at the ratios in the harmonic scale in the key of C. Remember that the harmonic series isn't a man-made tuning system. It's just the number series, starting with a tonic at 1 and forming intervallic relationships between numbered tones that are similar to those produced in the ancient Enneads and in stacking fifths. But though similar, harmonic ratios are simply unworkable in one spot, surrounding the problem note of F. But first, let's look at what the harmonic series gets right, which is everything else. The major third as E, or harmonic 5, tempers the chromatic scale by utilizing the 10 to 9 ratio between E at harmonic 10 and D at harmonic 9, a relationship that solves the Pythagorean comma. It does this naturally, simply by acknowledging the position of D and E in the series, and it's the first tuning system we've looked at that utilizes the 10-to-9 relationship here in its proper location. And the relationship at the end of the scale between B and C that's been problematic in earlier scales is fixed simply by using the 16:15 ratio produced by the harmonic series, where B enters the series at harmonic 15 and C scales up to harmonic 16. And yes, the problem note of F sits between the two ratios in the harmonic scale that are unworkable, 21:20 and 8:7. But if we look at this more closely, we can see that this section is actually Ptolemy's soft diatonic tetrachord. We didn't look at this one back at the beginning of the video, but it's another tetrachord, this time with intervallic ratios of 21:20, 10:9, and 8:7. Apparently, this natural progression was valuable enough musically for Ptolemy to cite and name, so can we really say it's unworkable? These are harmonic ratios, reflecting the notes of F at harmonic 21 to E at harmonic 20, and G at harmonic 24 to F at harmonic 21, a ratio that's identical, when reduced, to the relationship between C at harmonic 8 and B flat at harmonic 7. But perhaps, at least for the purposes of this diatonic scale, we can call these ratios unworkable. So putting Ptolemy aside, this scale that fails to use the harmonic mean of the demiurge to achieve a perfect fourth F scores only 5 correct ratios out of 7. Many researchers in the field of music theory have offered their recommendations for properly tuning a scale, and I'd like to focus on 3 of them. Joseph Sauveur in 1701, who gave us frequencies of the G major scale, which, like D major, avoids the note of F. George Biddle Airy in 1871, who gave us a list of ratios for the C major scale, and George Gurdjieff in 1915, who gave us a list of ratios for the Do-Re-Mi scale. Their scales all match the intervallic ratio of 10:9 between the major second and third that we see in the harmonic series. They use the 16:15 and 9:8 ratios surrounding the perfect fourth as the ancient Sumerians and Babylonians did. And they use the 16:15 ratio between B and C that, again, the harmonic series defines. But where I think they fail is in flipping the order of the apogdo, 9:8, and the grave, 10:9, surrounding the major sixth, the note of A in the key of C. We don't see this ordering of ratios in any other scale. The problem is that flipping these two ratios in the key of C prevents an A at 432 Hz. Instead, in the key of C, Sauveur, Airy, and Gurdjieff's ratio would tune A at 426.66 repeating. But 432 is the value for A that naturally calculates in both harmonic and Pythagorean tuning. It's also the value for A given in the ancient Sumerian, Babylonian, and Greek Hypodorian. But remember, those are D major scales, where A sits in the position of major seventh. In a C major scale, A sits in the position of the major sixth, and is therefore defined by this 10:9 ratio that precedes the major sixth. And this is why it's impossible to modulate between keys with any tuning system other than equal temperament, because A defined by the 10:9 ratio will have a different frequency value than A defined by the 9:8 ratio. Anyway, we could argue for years about why A at 432 should or should not be retained, but I've already made several of those arguments in other videos, so for now, I'd like to just listen to the resulting 4 chord in the key of C, comprised of the notes of C, F, and A, and compare the chords using A at 426.6 and A at 432. The 4-chord tuning A at 426.6 is flat, and we know it's flat because the A has been flattened by the 10:9 ratio sitting in the wrong spot. But using the ratios listed at the bottom of this graphic, preserving the 9:8 ratio that produces A at 432 gives us an open ascendant 4-chord. Finally, let's listen to the scale recommended by Sauveur, Airy, and Gurdjieff in the key of C, after which we'll hear the scale using what I'm calling the tuning solution, based on the correct ratios shown earlier at the bottom of the screen. Please let me know in the comments if you can hear a difference and if you have a preference. I'm grateful for any feedback. Please leave your thoughts in the comments, and thank you for watching.